Hello and welcome to project number 4 from the Easy FPGA course. In this project we are going to implement a Hamming single error correction double error detection circuit. Hamming codes are a set of error correction codes that can be used to correct 1-bit errors and detect 2-bit errors that can occur when the data is stored or moved between a sender and a receiver. It is a technique developed by Richard W. Hamming for error correction that uses redundant parity bits. Let's have a quick project overview. In part 1, we are first going to design in Verilog the following modules: a Hamming 7.4 and 8.4 encoder and decoder, a noise add module, an 8-to-3 priority encoder, a 7-segment decoder, and the Hamming SECDED top module. The top module is going to integrate all the other submodules presented before. After this, we are going to implement a Verilog self-checking test bench for the Hamming SECDED top, and next we are going to do a Modelsim project and a simulation to see how our module behaves. In the end, our project on the board will do the following. We will have 4 bits for the input data that is going to go in the Hamming encoder here, and next 5 bits for the noise module that is going to help us to alter 1, 2 or 3 bits. On the first 4 LEDs on the board we are going to see the value from the Hamming decoder, and on the last 3 LEDs we are going to see the 1-bit error, 2-bit error and parity error signals. Also, on the 7-segment display, we are going to see the value of the syndrome that points to the bit position that is flipped. So 4 bits of data are going to be converted into 7 bits by the Hamming encoder and also an extra parity bit. After this, we are going to be able to create 1-bit, 2-bit or 3-bit errors. In the end, our Hamming decoder is going to get 8 bits of data and is going to be able to fix a 1-bit error and signal it, signal a 2-bit error, or signal a parity error. In part 2 of this tutorial, we are going to create a Quartus project, synthesize the top module, connect the design to the FPGA pins, program the DE1 SoC from Altera, and in the end do some real-time testing on the board. This is how our experiments are going to look like. With iNoise of 3.0 we can create 1-bit and 2-bit errors, and with iNoise of 4 we can create a parity error. In this case we have an input data that has a value of 1000, which is 8. We trigger a 1-bit error on the 2nd bit from the Hamming vector. Our decoder finds this error, signals it here, and also shows us the bit position that was corrected. In the end, the decoder, after it fixes this error, is going to output on the LEDs the same 1000 value. This shows us in action the single error correction part of the circuit. Although this is a combinational circuit, it has several modules that were designed in previous projects from the Ovisign channel. You will be able to understand and replicate this project in Modelsim and on your board without watching them. If you want an in-depth presentation of the 3 modules within the red dotted rectangles, I recommend you watching the tutorials attached in the video's description. The 7-segment decoder is presented in FPGA project number 3, binary adder to 7-segment display. The Hamming encoder and decoder are presented in how to implement a Hamming 7.4 decoder for FPGA using Verilog, and how to implement a Hamming 7.4 encoder for FPGA using Verilog. Let's say Alice wants to send a 4-bit message to Bob. During the transmission over the noisy channel, you could have no errors, 1-bit error, 2-bit errors, or multi-bit error. 2-bit errors and 3-bit errors occur less frequently than 1-bit errors. Let's say that Alice uses a Hamming 7/4 encoder. From the 4 bits of input data, she will get 7 bits of output data. During the transmission, let's say that bit number 5 was flipped. Bob uses the Hamming decoder, and the decoder will detect automatically that bit 5 was flipped and will fix it. Hamming codes are widely used in telecom, computer storage, and ECC RAM. The most important part in the decoder is how we interpret the syndrome value and the overall parity. This gives us the error type. When we have a syndrome of 0 and an overall parity of 0, it means that we have no error. The overall parity is calculated by doing an XOR between the I data and the I parity. If the syndrome is different than 0 and the overall parity is 1, this means that we have a 1-bit error. The syndrome shows the incorrect bit position and it fixes it. Please note that in case of a 3-bit error, the 1-bit error could also assert. 3 or more bit errors are not correctly detectable or correctable. When the syndrome is different than 0 and the overall parity is 0, this means that we have a 2-bit error which is not correctable. Even if this type of error is not correctable, in safety-critical applications it is very important to signal this to upper-level decision-making systems. In the last case, where the syndrome is 0 and the overall parity is 1, this means that we have a parity error. The data is already correct, but only the parity error flipped. Let's see how a Hamming encoder and decoder can be implemented without entering inside the interesting algebra behind it. Hamming codes rely on parity bits generated from the input message. If we want to be able to generate a code word for n input data bits, then we require k parity bits in the output data. Hamming encoders and decoders can be adapted to the size of the application they are being used in. For example, for a bus width of 4 bits, you need a Hamming 7/4 encoder, or for a bus width of 247 bits, you need 255 bits in the output data. Let's see how the parity bits are created for a 7/4 encoder. As you can see here, we have the data bits, and inside the encoder we use some XOR gate to create the parity bits. The parity bits are arranged inside the positions that are power of 2, meaning 1, 2, and 4. Inside the decoder, the same message that was encoded over here enters, and using other XOR gates, the parity bits are recreated, and then the syndrome is computed. If we have an error, the error will be fixed by XORing the value of the syndrome with the value of the input message. If we have no errors, then the message will remain as it entered the encoder. The noise add module is a design for testability module. It creates no bit, 1 bit, 2 bit, or 3 bit errors for an 8 bit input bus. 1 bit error means that bit number n was altered using an XOR operation between its value and a noise vector. iData is an 8 bit input bus that contains the Hamming 7/4 code word and the input parity. iNoise is a 5 bit input bus connected with the switches. Bits 2 to 0 are used to generate 1 bit errors on OData. These are correctable by the Hamming decoder. Bit number 3 is used to generate 1 bit or 2 bit errors on OData. 2 bit errors are not correctable. Bit number 4 is used to generate parity bit errors or 3 bit errors. OData is an 8 bit output bus that contains the data with or without errors. And now it's action time! Please create the following Verilog files. We have 6 Verilog design files and 1 Verilog testbench file. You can also pause the video and write the content of each file to get the full hands-on experience of this tutorial. Note that the full project can be downloaded from ovisign.com/courses. Please make a new file called noiseadd.v with the following content. The noise add module can be designed in multiple ways, but I choose this version because it helps us demonstrate the capabilities of Hamming codes on the DE1 SoC development board. At line 30, I declare the noise variable that is going to be used inside the always at start procedure. This will synthesize into a combinational circuit that will do the following. Use iNoise of 20 to generate a 1-bit error at a specified position using a walking 1 pattern. Use iNoise of 3 to generate a 1-bit error at bit 6 or a 2-bit error if iNoise of 20 is non-zero. Use iNoise of 4 to generate a parity error or a 3-bit error. The wire from line 32 is used only for simulation and debug purposes, and it won't generate any combinational logic after synthesis. Let's now create the priority encoder. The priority encoder will show us the highest index of the bit that is set. The D input of this module is connected with the syndrome value from the decoder, which is a 1 hot value. Q and V are declared as output reg because they are used in the left-hand side of an always at start procedure. The case 1 evaluates the first bit that is set in descending order of the index and outputs the position and the valid bit. We don't use the valid bit in our design, but it can be used in other projects where the functionality requires it. Remember that I've oversimplified the descriptions of these modules to make the tutorial more time efficient. If you want to be able to easily design digital circuits for FPGA or ASIC using Verilog, I gladly recommend you my course Verilog HDL Fundamentals for Digital Design and Functional Verification. The course can be found in the video description. Let's look now at the top-level port description for the Hamming SECDED. Here we have two input ports. The SECDED input port is used as input data for the Hamming encoder, and the iNoise port is used to generate 1-bit, 2-bit, 3-bit, and parity errors. As for the output ports, we have 4 bits for the SECDED output coming from the Hamming decoder, 7 bits used to control the 7-segment display, and 3 bits for the errors, 1-bit, 2-bit, or parity error. Let's have a look now over the Hamming 7.4 Verilog code. Here we declare the module I/O ports. These variables are used to create the combinational logic for the parity bits. In part 2 you will see how this is translated into a logic gate circuit by Intel Quartus. In the end we concatenate the input data bits with the parity bits to obtain the output data value. If you want a detailed description of this module, please look at the Hamming tutorial from the video description. Now let's analyze the code for the Hamming decoder. This is a bit more complex, but it does the following. It calculates the parity bits over here. Next it calculates the syndrome based on the parity bits. After this, we fix any 1-bit errors based on the syndrome value and the input data. This bus is used only for debug to see it in the simulator. Here we calculate the overall parity. And here we have the 1-bit, 2-bit and parity error bits. This code over here can be optimized even more, but I decided to leave it like this to have more clarity. In the end, we reconstruct the output data based on data decoded. Here you have the code for the 7-segment decoder. This code is thoroughly explained in FPGA project number 3. The top-level module looks like this. We have our module ports that are previously described. Next we have some internal logic. They are used to interconnect several sub-modules inside the top-level module. The first module is the Hamming encoder that takes the input data and outputs the Hamming code and the parity. Next we instantiate the noise add module and connect it with the Hamming encoder outputs and the Hamming decoder inputs. And after this we instantiate the Hamming decoder. Here we have the priority encoder used to translate the syndrome value from 1 hot to binary. In the end, we instantiate the 7-segment decoder and connect it with the output of the top module. This is it. Let's take a look over the Testbench code. We first declare 2 defines that are going to be used for our self-checking test bench. If we expect no error, then we should have a 0 value. If we expect an error, then we have the 1 value. After this we declare the timescale and next the testbench name. Here we have the testbench variables. We use reg for the inputs of the DUT and wire for the outputs of the DUT. Next we instantiate the DUT and connect its ports with the testbench variables. After this we have the test scenario. In the first test we don't insert any errors. This test helps us see that the output of the decoder is the same as the input of the encoder. We use a for loop to sweep on all the values on 4 bits from 0 to 15. Here we change the value of the input variables, we wait 1 nanosecond, then we compare the data with the expected value. We expect to have no errors, and the input should be equal with the output. This is a small pause between tests. And now we test 1-bit errors. For values from 0 to 15, we change the noise vector to have a random value between 7 and 1. These will trigger several bits from the 1 hot error vector. If I equals 16, then we are setting a parity error. We wait 1 nanosecond also, and then we compare the data. The input should be equal with the output, a 1-bit error should be signaled, and the other a true error should be 0. For the parity error, the input should be equal with the output, and only the parity error bit should be set. Now we take another pause between the tests and trigger 2-bit errors. This is how we trigger a 2-bit error. We set bit 3, and then we put a non-zero value on bits 2 to 0. We wait 1 nanosecond, and then we compare the data. We expect to have a 2-bit error. Here we trigger a 3-bit error. To do this, we need to alter the parity and set a 2-bit error. We don't validate anything here, but we are going to observe what's happening on the wave. In the end, we do another test that has no errors. The input and output data should be equal once again. In the end, we print the statistics counters. If we have no errors, success count should equal test count and error count should be 0. This is the task that is helping us validate the functionality of our module. If we are not expecting a 2-bit error, then the input data and the flags should be equal, else if we are expecting a 2-bit error, then only the 2-bit error flags should be equal. We don't care about the data or the other flags. You should play a bit with the testbench scenario to see what happens. Let's create now a Modelsim project and simulate our testbench. We are going to use the same folder structure that we used in the other projects. Next, we are going to create a Modelsim project inside the sim folder. Let's open Modelsim. File, change directory. Select folder, file, new, project, type here project, okay, add existing files, we go 1 level up and select everything, click OK, close, we see the files added to the project and compile all. See that all the files were compiled successfully. Now we press Simulate, Start Simulation. Expand the work library and select the test bench. This is our DUT that has 5 submodules. We are going to add in the test bench only the encoder, the noise module, and the decoder. The other 2 modules are previously tested and we are going to see them on the FPGA board also. We create a new divider, press OK, and then we add all the signals from the encoder. We press this. Now create other dividers for the noise and the decoder. In the end, your wave should look like this. Now press Run All. If we analyze the test statistics, we can see that our success count is 50, our error count is 0, and our test count is also 50. So the test was a complete success. So this is how your test should look like in the end. Here we can see how the input data from the encoder equals the output data from the decoder. We test all 16 possible combinations on 4 bits. In test number 2 we have the 1-bit error scenario. Here we can see that the syndrome starts getting non-zero value because it corrects data according to the error that it finds. O data also equals I data over here. During this time you can see that the noise module is quite busy creating the 1-bit errors. If we look at the syndrome, it's pointing the 1-bit position where the error happens. Also here, the O1-bit error flag is asserted. Now let's analyze test number 3 where we have 2-bit errors. You can see that the O2-bit error flag is asserted and the other 2 are cleared. Here the noise module generates 2-bit error according to the iNoise vector. You can see how the input data and the output data are different now because the decoder corrects in a wrong manner the data based on the syndrome. As I said, 2-bit errors are not correctable, but they are detectable. Here we have the 3-bit error. You can see that the data has this value, but when it exits, it has 3 different bits. This one, and this one. Our decoder incorrectly outputs O1-bit error. Our decoder signaled this with O1-bit error, but the input data and the output data are different. This is also expected behavior. In the end, we do again a test with data that has no errors, and we can see that the encoder and the decoder work correctly again. If you like this tutorial, please press the like button and subscribe. If you like this tutorial and you're interested in an easy path for learning Verilog for FPGA or ASIC design and verification, I gladly recommend you my course Verilog HDL Fundamentals for Digital Design and Verification. You can find the link in the video description. For more tutorials and support, you can join our Facebook community. Your strong Verilog foundation is only one click away.